Hello, everybody. My name is Pavan Turaga, and I'm here today to talk to you about a landscape of the time series analysis methods. So this class is a module from the T32 grant that we have on system-space modeling for precision nutrition. So in this lecture, I actually have two computers, and therefore you are seeing me in two different, profiles, but it's really just me in two different places, one on my laptop and one on my desktop. And I'll be going back and forth between the two to share different types of things. To start with, a little bit about me. I am Pavan Turaga. I'm a professor in the School of Arts, Media, and Engineering, and have a joint appointment in electrical engineering at Arizona State University. I run a lab called the Geometric Media Lab, which specializes in geometric techniques in machine learning as applied to different types of data, including sensor data, time series data, image data, video data, 3D data, all kinds of stuff. What does geometry mean in this context is a whole other story, and I might touch upon a few of those ideas as we talk through this lecture. But this lecture is more broad, and it's about the broad bucket of time series analysis methods as it's relevant to health and nutrition and so on and so forth. So let's start with where do time series appear in health and wellness and precision nutrition? In my experience, I'm an engineer, so I work with a lot of other researchers who do health and nutrition work, and always, the beginning of the analysis pipeline is the choice of a sensor. Sensors are many, depending upon what you want to measure. Sensors range from accelerometers that measure movement, pressure sensors that measure things under your feet, pressure or other sensors such as temperature sensors of the body, continuous glucose monitors that measure other biomarkers inside the body. So there is a diversity of sensing mechanisms and sensors that are measuring different properties of the physiological system, that is the human body. When we record data of this type, it creates very interesting situations on one hand, which are related to very simple things like the sampling rate of a time series sensor. What do we mean by sampling rate? Accelerometers that most of us are familiar with, such as the Fitbit, will operate at 100 hertz or 200 hertz, something in that range. When we say 100 hertz, it means they're measuring 100 individual samples per second. Of what? Of that physical quantity that it's designed to measure. If it's an inertial measurement unit, it's measuring some kind of acceleration or a force kind of measurement in a particular axis. If you have a 100 hertz sensor and so let's say it's the Fitbit and you attach it to your body and you're off in a free living condition and you're doing 24/7 recordings, it creates enormous amounts of data. 100 samples per second. A 1 minute wear would give you 60 times 100, 6,000 samples. A 1 hour wear would mean 6,000 multiplied by 60, and it just keeps on going. So when we talk of raw time series data analysis, the challenge becomes increasingly hard the longer you keep recording data. And so there is, however, certain canonical frameworks that people talk about when they say time series analysis, and I'll talk about this, which are commonly occurring and relevant to our lecture. Many times, the most common thing that you will encounter very early on is this question of classification, which is the bottom panel here. And we'll get to that in a little more detail very soon. But time series analysis is more than just classification and categorization. One of the things that people talk about time series analysis is forecasting, which you may have heard of in other contexts like weather, stock price, this and that. But even in health and wellness, sometimes people do talk about forecasting. Maybe not the raw time series of an IMU, that's not particularly relevant. But if there is a slightly more processed time series that converts your variable data to activity counts, could you use that to forecast typical behaviors into the future and measure if the actual measured behavior is deviating from the predicted one and create certain flags if such is the case. So time series forecasting is one big bucket problem area that people talk about. We will not talk about this in our lecture today much. The other very common thing that happens in wearables and health and wellness types of data sets is that time series is measured, but there are gaps in the data. And this happens because of a number of reasons. If you might be wearing a Fitbit, maybe it ran out of battery for a couple hours and it had to be charged. So it didn't measure anything for 2 hours. So you'll see a gap in the data. And that's the second panel that you're seeing. Or there may be other flaws in the device itself. Maybe it lost access to, I don't know, Wi-Fi and it didn't transfer data and something was lost into the ether. So all kinds of unexpected situations occur in regular daily use of wearables. And these are often known as, data with gaps. And the technical term we use to fill in that missing data is called imputation or time series imputation. It is very connected to forecasting because if you're imputing data with only what you've observed, it's pretty much the same as forecasting. But in the imputation method, you have access to not only the immediate past, but also the immediate future of the window that you're trying to fill in. So you have a little extra information. But many of the methods are often very similar. So many of the mathematical techniques are very similar for forecasting and imputation, except you use extra information from the immediate future to look backwards, for example. But data imputation is a common problem. We have seen that many times in data sets that we have worked with. Yeah, we will not get into the forecasting imputation in much detail today. The other big bucket is anomaly detection. This happens a lot in, this slide, of course, is industrial maintenance because this is from a survey paper on time series analysis methods, but it happens all the time in like ECG data analysis or EEG data analysis a lot, where you have some expected rhythmic oscillatory behavior and something fundamentally changes, and maybe it's indicative of a stroke or cardiac arrest or epilepsy or whatnot, epileptic seizures. So there is anomaly detection, which is a huge bucket area for time series analysis. The challenge there, however, is that we have not yet been able to define in clear ways what anomalies mean. They mean different things in different contexts. They mean different things depending upon the sensor, depending upon the health condition of interest. So mathematically, as a methodology, anomaly detection still does not have a unified framework that I can just present and say, this is how you do anomaly detection. It's a very integrated endeavor with time series modelers and clinicians and other folks who think about anomalies and what they look like in that situation. The bottom panel is classification, for which when we say classification, it's converting a given time series to one of K categorical labels, very commonly exemplified by activity recognition. So you might be wearing an IMU and you want to recognize what activity the person's performing from a list of 10 expected prescribed activities. And this is a very, very canonical time series modeling problem. And it happens, examples of this problem appear in many, many, many areas of health and wellness, fitness tracking. In precision nutrition, you may be interested in looking at also the physical activity and what it might indicate about nutrition cycles or the correlation between blood glucose and physical activity and so on and so forth. But beyond just precision nutrition, classification is also very commonly used in all kinds of health conditions for detection of a specific disease condition. For example, you might be looking at gait, and based off of a little gait test, you might want to classify whether the person shows symptoms of Parkinson's or not, or you might take a speech recording, and from the speech recording, which is also a time series, you might want to recognize early signs of Alzheimer's or not. So time series classification has many, many, many applications in general health and wellness, but also in precision nutrition. We will spend some extra time today on the classification problem and look at some very quick toolkits that you can play with today. And we will get to the toolkits first, as opposed to go through a ton of theory. We'll look at the toolkits, give you an assignment, and then we'll introduce a little extra theory to say, oh, hey, look, these are convenient things, but there are problems in these frameworks and how you can advance them through advanced research methods. With that, Let's look at time series classification as an abstraction. In time series classification, the beginning is often always a raw time series that's been recorded through a sensor. Okay, so, and from that time series, uh, we often like to compress the time series. Like I said, if it's a 100 hertz sensor and you're recording it, let's say you recorded it for an hour, you cannot take the whole hour and classify it into something meaningful for activity recognition. So you might end up doing windowed analysis, right? You might take 1 minute windows at a time and try and classify what the person was doing in that 1 minute. But even at that 1 minute level, you have 6,000 samples at 100 hertz. So dealing with 6,000 samples is still a problem. So we use this this phrase called extract features or feature extraction or featureize or some variation to that to refer to essentially a way to compress these 6,000 numbers into something more manageable. And by manageable, typically we mean a dozen maybe or 20, 30, something like that. Things that may have some intuition encoded into them, things that may actually have some physical interpretation. Now, what kind of features do we talk about when we say that? So one of the things I'd like you to know is this field has undergone a dramatic transformation in the past decade. So pre-2010, if I were talking of extract features, I would talk about the things you're seeing here. We'll say, oh, let's try to normalize the range of the time series into some standard range, 0, 1. Look at the average values, subtract the average. If there is a trend in the time series, remove the trend. It's called detrending. Let's look at only the fluctuations that remain after the trend has been removed. So those kinds of things. And then once you have removed some of these nuisance factors, then let's look at some features like the Fourier transform, which is a way to decompose oscillatory signals into a small set of energy bands in the frequency spectrum, which can be explained roughly, right? I mean, if you take a time series and if you're looking at someone walking at 4 miles an hour and the sensors attached to their wrist, you will see a quasi-cyclic pattern in the observed time series, which can be explained as if there was some basic repeating frequency element in that time series, and the energy in that frequency band could be a feature. How much energy is there in that feature band, and then how much energy is there in the nearby feature bands, and so on and so forth. So this type of analysis is still done. It's not like it's gone, but this type of analysis is, I would say, still pre-2010s. It requires some understanding of a few signal processing toolkits, like decomposition, trends, and trend analysis, removing if like the detrending is very common in time series, which seem to generally keep going up all the time and then keep going down all the time. These are not oscillatory signals. For example, if you look at glucose monitoring, our glucose monitoring doesn't oscillate through the day. It has trends. It spikes around, right after you have a meal and then slows down and then spikes again. So there is a trend there. But if you want to look at some finer details, is there actual fluctuations embedded within that trend? Then you have to do detrending, decompose, look at the oscillatory patterns, and then make some assessment from there. For other sensors like IMUs, we don't have trends. I mean, IMUs are really measuring acceleratory features, and as you move, you see oscillatory patterns anyway. So that's different. So depending upon the sensor, sometimes you have to pick and choose what pre-processing tools you need. But then when you come to the features themselves, the big bucket features are really Fourier features. These are extremely commonly used in activity recognition. And these are really a frequency decomposition of the measured time series into different bands of frequency energies. Very commonly also used in speech analysis. If you take a speech signal, we commonly decompose our speech into certain frequency bands, and we can interpret them. In the speech context, it's easy. We have very easy interpretations that audible speech is in the 4 kilohertz to, 400 hertz to 8 kilohertz, that kind of range. And beyond that is finer and finer, patterns in speech. So we can try and interpret some of these things if these things are done carefully. This entire endeavor of constructing features is also now called feature engineering. It's still a very active endeavor, and there's dozens and dozens and dozens of features, no dearth of them. But once you have made a choice of a feature, to take the 6,000 numbers and then you pass it through a feature extractor, and maybe it brought this down to a number of, a set of 30 numbers, you still have this problem of converting these 30 numbers to your K categorical labels. Let's say it's activity recognition, really, and I want to convert my time series to uh, one of 10 activity labels like walking, swimming, running, jogging, reading a newspaper, having coffee, sitting down, sedentary, just sleeping. So if I come up with a list of 10 activities, I'd like to know from these compressed set of features, what are the correlations between being awake or being sedentary or being in a running state, and what does that imply on the distribution of these features in this 30-dimensional feature space? So to come up with these decision rules that, oh, if you're in this upper quadrant in, let's say, if you take feature number 51, or you take a plot of feature number 2 versus feature number 5, and you see that all the walking features are clustered on the top right, all the sleeping signals are clustered on the bottom left, then you have a decision rule, and you can express that decision rule in many different ways, either through linear classifiers, or if the boundaries are not clear, you can have other non-linear classifiers like decision trees and other things like perceptrons, which are a simple form of a neural network. So this slide summarizes activity recognition and actually time series classification pre-2010. All new novel contributions were happening at extracting new types of features and extracting new types of classification rules from those features. Post 2010, things have changed a little bit. You may have heard of this revolution called deep learning. So we will dive into that a little bit. Rather than start from the classics and never get to deep learning, my approach today is we'll start with deep learning, and then we'll work a little backwards in filling in gaps that deep learning can be improved with. So this notion of extracting features and then plugging the features into a classifier has been kind of appended by this joint approach, which I'm writing this as a feature learner plus a classifier. What do you mean by a feature learner plus a classifier? So this combination of the two is really what people mean when they say deep learning or a deep neural network. What does that mean? It's very commonly exemplified in the case of time series. There are, again, 4 or 5 types of deep learning models. We cannot survey everything, but we'll start with a very common one, which is called a temporal convolutional network. And I will expand that in the next slide. So a temporal convolutional neural net works like this. If you look at the blue nodes on the bottom, those are your raw time series values, where each node, each circle, in neural nets, we refer to things as nodes and layers and so on and so forth. So when I look at the input layer here, this input layer is the raw time series, the 6,000 samples that we are talking about. We are not going to use a feature that we thought through and brought down from 6,000 to 30 and then plug it in. That's not what we're saying here. So this neural network is going to work straight on the raw time series, the 6,000 samples directly, which means the input, in this case, in the example we are talking about, it will have 6,000 blue dots on the input layer. So every blue dot represents one time sample, and the value on that is in that node. The second layer, which is being referred to here as a hidden layer, dilation equals 1. So we'll get to what all these things mean very soon. But the way the hidden layer is working is, look at the flow of these arrows. So 2 blue dots are connected to this one dot, one circle in the hidden layer. So this is, you can imagine that these 2 layers, these 2 values are being averaged in some weighted average sense. And that weighted average value is sitting in this circle that it's connected to. Now, what are the weights of those averages? By weighted average, we mean wild things. We don't simply mean, oh yeah, take this value and take the next value and just hit them with zero point 0.5 and 0.5, add them up. That's not what we're saying. So the weights of averaging can be learnable. And in a neural network, it's not gonna use simple weights like 0.5 and 0.5. It will try and learn through a process called training what might be the optimal weights of combination that lead to the highest classification accuracy. So that's the training process of a neural net. The weights are not shown here in the picture, but the weights of combination, you can imagine them as little numbers sitting on these arrows that connect. So maybe the optimal weight after training might look weird. Like maybe this value is, oh, my mouse. Okay, maybe this value ends up becoming 0.612, and this value becomes 0.221. I mean, there is nothing that even says they have to add to one unless you constrain the neural net in certain ways. But the reason why it's called a convolution is if you shift to the right by 1 unit, okay, if you shift to the right by 1 unit, so these dotted lines that you're seeing, oops, I'm having a little trouble with my mouse, so please excuse me. So if you look at these two contribute to this circle, these two contribute to this circle, and so on and so forth. So these two will contribute to this circle. Now the weights of combination are replicated across these nodes. So if this ends up being 0.612, then if this is 0.612, then so is this, and so is this, and so is this, and so is this, and so on and so forth. If this value is 0.221, then so is this one, and so is this one, and so is this one. So there is this tying of weights, which makes this process qualify to be called a convolution. A convolution is the word convolution comes from a very basic core signal processing concept, which is a way to implement filters of different types, which we may refer to in common language as smoothing filters or reverb filters or sharpening filters. So there's many ways in which we understand this convolution process when it's applied to speech. And even for image data, there are equivalents. You do the same kind of convolution, weighted averages on a 2D grid, and we interpret those convolutions as concepts like blur or unsharp masking or edge detectors and so on and so forth. So convolution is a particular term that comes from signal processing. It refers to weighted averages of different types. And the reason, the distinguishing feature of something being a convolution is that, yeah, there is a small set of two weights here. So this is called a convolution with a kernel of size 2. So two values on the input combine to give one value in the hidden. But then the two combination weights are held fixed when you shift to the right. So as you shift to the right, the combination weights are the same as the combination weights here, and so on and so forth. And now this process is repeated across multiple levels. Now the thing to note is if you have 6,000 samples on the input layer and you did this a convolution of kernel 2, like two values combined, then you have a little engineering issue that what happens at the very ends, right? I mean, when you keep shifting, at the very end, you run short of a sample, so the hidden layer can shrink. There's probably one less output. So there are little details, and in the neural network world, there are ways to deal with them through things like padding on the outsides and so on and so forth. To keep it simple, in this graphic, things will stay the same. So meaning the number of nodes will stay the same as you go up in the chain. So if there are 6,000 blue dots, there will be 6,000 white dots in the hidden layer 1. And there will be, yeah, so on and so forth. So now you can have this concept of dilation to reduce the number of features. You can choose to shift not by 1 unit at a time, but you can have things that are 2 units apart connect to each other right? In this case, neighboring units were contributing to one white circle, but here, two units which are separated by another one is contributing to this one, okay? So this is called dilation 2. And then there is another concept called strides, where the shifts that we're doing by 1 unit at a time can happen in 5 units at a time. So that can also reduce the number of valid values in the middle. So the idea here is simple, that a time series is input, and you have these weighted averages that are happening pairwise at a time to keep it simple. And then the next layer looks also like a time series. And then you process it again with another convolution to make it another time series, and again to make it another time series. At some point, we have to structure these operations in very careful ways, because at the very output, if I have a classification problem with, let's say, 8 classes or 10 classes, I need the output to be no more than the K values that, the K categories that I'm interested in. The hope is that we do what is called a one-hot encoding of the classes on the output. If there are 10 categories, I want the corresponding, if it's class number 10 that's coming in on the input, I want the 10th value on the output node to have a high value and everything else to be zeros. So that's called a one-hot encoding. So typically, it's very common in these convolutional neural nets to have the number of output nodes to be equal to the number of classes we have. And our engineering problem is then to structure the rest of the network so that the 6,000 samples slowly shrinks in size in some structured way to give you 10 numbers on the output. And that can be done through many tricks. Adding this dilation and strides is one trick. Adding other operations called max pooling is another way, and there's many tricks to this trade. So this is a very classic example of what is happening these days. Post 2010, time series classification by default seems to be neural networks of this type. What we're seeing is a convolutional neural net. There are other types of time series neural nets, like recurrent neural nets, long short-term memory neural nets, transformer architectures, which are not as straightforward as this one, but they all come from different communities. You know, they are inspired weakly by neuroscience studies or language studies, and some of them can be very involved, but this is the beginnings. We'll take a little pause right now, and I'll switch my screens because I want to walk you through the assignment we have for you, which would be to try and work with a pre-existing Python notebook on this tool called Google Colab to try and run and train a neural network and play with its parameters a little bit and see what happens. So let me pause it for just 1 second, and I will shift to my other screen. Okay, replace with this one. All right. Okay, reconnect. So you should have access to this Google Notebook, which will be shared as part of your assignments. It says copy of time series classification from scratch. So when you click on the link that will be provided, if you have never opened this interface called Google Colab, nothing will appear like this. You will see all garbage. But look for this sign, you know, on this top left, which says CO, standing for Colab. That sign will appear somewhere in the middle of your screen. It will give you an option, open with Colab. So just open with Colab, and this is the interface you'll get. When you get it opened, so this is sitting in my Google Drive. We want you to make a copy in your Google Drive. So you would go to File and say, save a copy in Drive for yourself. Call it whatever you want that you can find easily. Save this copy, because if you start editing this file that's shared, then it will edit it for everybody. So don't edit it for everybody. Make a copy for yourself. Save a copy in Drive. One thing we want to do is go to this runtime menu, and under, okay, not manage sessions, but look at runtime and change runtime type. Make sure your GPU is selected. Now, this might look a little different if you are using ASU Gmail account or if you're using your personal Gmail account. I recommend using ASU Gmail account because that's what I've tested it with. If you go to your private Gmail account, these options may look a bit different, but choose a GPU that's available. So step one, do nothing, but go to runtime and hit run all and make sure the whole thing runs with no problems. And then I'll step you through what's happening in each part of this code. So what you're seeing is a Python notebook. Everything is written in Python, and the package for machine learning that's being used is Keras, which is a very popular, library of deep learning tools. I wouldn't consider myself an expert in Python or Keras, but I'm trained as an engineer, so I got a lot of experience working with MATLAB and stuff like that. And Python is similar to MATLAB, but this is more user-friendly than coding in C, C++. If you want to code it from scratch, yes, you will have to do hours and hours of Python tutorials. But if you want to just get a sense of how machine learning works, these free toolboxes and Python notebooks, they abound. They are plenty. So just learn to run through them. So read through the descriptions. This is loading a standard data set from the UC Irvine, data set, UC Riverside, It's not a health-related data set. It's some time series data set which deals with engine noise and classifying a recorded signal as anomalous or not. So it's a binary classification problem. Many time series have been collected and labeled by human experts on whether this time series whether the engine noise captured by this motor sensor indicates a problem or not. So it's just binary, yes, no. So the dataset has 3,601 training instances. When they say training instances, it means 3,601 time series have been, individual segments of time series have been given as training examples. And 1,320 are given as test examples. So you read the data in the data format. Writing a data loader can take work from scratch, but we are just working through a simple example. Quick visualization of data. It looks like when you say binary, you can call them class 0, class 1, or class A, class B, or class -1, class 1. In this case, they're calling it class -1, class 1. And class 1 is presumably normal, class -1 is a problem. So visually, you can't really make a decision rule just by looking at the time series, and that's why machine learning is important. Point to note is each time series has 500 samples, as this picture shows. So they're going to create a train and test set from the sample. That's fine. Keep going through. Now get to this point where it says build a model. This is the core of where a neural network is being built. It starts with this function called def make model input shape. And all these things will be hard to read, but you have to go back and forth between what this is saying and its visualization down below. So step one is to see that this code block ends with two things: model.summary and keras.utils.plot model. So model.summary is this table that you're seeing. It's in table form. It's telling you what's happening in each layer, what is the size of the input in each layer, size of the output in each layer, how many trainable parameters there are. Remember in the example where I said, if you have a kernel of size 2, there are typically two values that you're trying to optimize for, so 2 parameters per kernel. Now in Keras, in addition to kernel values themselves, there is something called a bias term, and I'll talk about that real quick. Step one, input layer is 500 sized time series, right? So every instance of time is a node in your input. So the input layer takes the time series and spits out a 500 dimensional vector as is, just putting in every time instance as a value in the nodes. So the output shape is 500 times 1. So 500 rows, 1 column. Then you do what is called a convolution 1D. Here it doesn't say what is the kernel size, so you got to go back to the code and see what is happening in con1, this line 5 in the code block. Filters equals 64, kernel size equals 3. So arbitrarily, this model designer has said, I want to take my 500 dimensional time series and process it with 64 filters. Why 64 filters? We do not know. And in deep learning, this is all too common. You get to claim success because a model works, not because you can explain the model. So part of your exercise is to poke around with these numbers. Why 64? Why can't you do it with 1? If you change that to 1, what do I need to do elsewhere? That kind of stuff. Why kernel size 3? So it's processing 3 samples at a time, averaging them and shift, 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 shift. So if you have 64 filters and each filter is of size 3, you would say the number of trainable parameters is 64 times 3, which would be 192. But in Keras, whenever you do a convolution, there is also a bias term that's added. So you do this 3 average, and then you plus add a little bias term, which is also a trainable parameter, but the bias term is also tied together across all the shifts. So if someone says kernel 3, there are really 4 trainable parameters, the 3 weights, and then there is a bias term. So the number of trainable parameters in this one line of code is 64 times 4, which is 256. So in the model summary, that's what it's reporting. So the first con layer has 256 trainable parameters. The second line of code is a batch norm code, which tries to compute summary statistics like mean and standard deviations across channels, and that has you have to check through the math real carefully to make sense of these trainable parameters, but trust us and believe these numbers to be true. But somewhere along the way, things start blowing up. So once you're past this first con block, the output is, so batch norm, batch. So the output is now, so a 500 time series went in, it was processed by 64 filters. So now you have 64 time series as outputs, each of size 500. So you have a tensor of size 500 times 64. That's what they would call it. So the next block will have a hard time in dealing with it, and things start blowing up, therefore. So con 2 is once again process it with another set of 64 filters. Now the whole tensor, 64 times 500, is being processed by a whole other set of filters, 64 other filters. If it were one filter, this is what would happen. So the 64 times 500 with a kernel size 3 in a convolutional neural net, even if you say kernel size is 3, because now the input is a tensor, you have to add a vertical dimension for the math to work. So because the vertical dimension has 64 channels, a kernel size 3 really means you have 3 times 64 parameters, which 3 times 64 is, whatever, 192. But it's 3 times 64, but you also have the bias. So there's 4 learnable parameters, including the bias. So 4 times 64, 256 learnable parameters, again, per filter. And there are 64 such filters. So it's 64 times 256, and the numbers start blowing up. Okay. The number of trainable parameters here suddenly is 12,000. So in total, if you run through these numbers very carefully, take some practice to look at these network blocks, understanding how many parameters there are. So this is a very useful exercise to go through. And to help you out, it's giving you in total, there are 25,474 trainable parameters to classify one time series of size 500. Is it overkill? I mean, in the machine learning, deep learning world, this is contemporary conversation. Is it overkill to have a network that has 25,000 parameters to learn, all to classify a 500 dimensional time series? So these are big high-level theory questions, philosophy questions, but at this time, the understanding is, yes, the more parameters you have in your model, the more easily you can generalize it to more classes, to more challenging data sets. The more compressed your models are, they tend to be a little, they tend to be robust, but they tend to not be flexible to change to differing conditions. If you keep scrolling down, you'll see some test statistics. You'll see this concept called epochs. So to train a neural net, you do passes through the data set. You pass the data set several times through the neural network. Each time you pass the whole training set one full time is called one epoch. So you're passing the training set 500 times in sequence through the neural network. At every time, the neural network starts with a random initialization. Remember the 25,000 trainable parameters we have? They're all initialized randomly, like random samples. You just sample them between some values, -1 to 1, or some from normal distribution. and you do what is called a forward pass. You pass all your training examples through the neural net, and at the very end, you have your 10 vector. So let's look at this one. At the output shape, at the very end, you have this layer called a dense network, which is very good at compressing arbitrary sized inputs to specified numbers of outputs. We want the output to be of size 2 because it's a binary classification problem. It's a yes, no type problem. We want just 2 outputs. So, and those 2 outputs are one hot encoded. So in the training examples, if the sample is not problematic, maybe we call it 0, 1. And if the sample is problematic, we call it 1, 0. So that's a one hot encoding of 2 categories. And if something is in the middle after training, maybe you'll see a 0.5, 0.5 as output. So that allows for these intermediate steps, intermediate stages to be also accounted for. In any case, so you go through this forward pass and you compare the predictions of the network with the one hot encodings that were provided in the training set. And there is probably going to be error because you randomly initialize the network, they will not match. So that error is summed up over the entire training set and is called the loss function. The job of the neural network training algorithm is to tune all the 25,000 parameters to drive that loss function to 0. And there are some efficient ways to do it, some not so efficient ways to do it. But here it's all done through a technique called backpropagation and Adam optimizers. So these are all technical things you might learn if you take a class on machine learning. We want to call your attention to these diagnostics that it prints. After each epoch, it prints the loss value. The loss value is the sum of all errors in the predictions. That typically keeps going down. So if you keep looking at it, it probably starts high. Let's start at the beginning. So epoch number 1 starts at 0.6, and at the end, it has stopped after 500 epochs at a value of, oops, it didn't even go 500. There are some criteria it met and it stopped. It went down to 0.04. So it went from 0.6 to 0.04. So that's significant reduction. It's also giving what is called validation loss and validation accuracy. So as part of training sets, you also hold out a part of your training set and call it a validation set. You don't use that validation set to train the network, but you test it on the validation set before you test it really out in the world. So the validation loss or validation accuracy is a good surrogate of how the model might do when you let it out into the wild, so to speak. And the validation accuracy is a number between 0, 1 or 0 to 100%. And ideally, we want this to be very high. So at the very beginning, it starts with a 47% validation accuracy. And at the end, it ended up with a 97.5 or more, 97.23 in terms of validation accuracy. So that's good. So you want to drive the validation accuracy high, the validation loss low, the training loss low. So those are the types of diagnostics you're looking for. And often always there is a third held out. So in training set, there is a training set and a validation set. And after you freeze training, so you can use the validation loss and the train test loss to create these early stopping criteria. Typically, what happens is here, in the part of the training, you have a subset called the validation set. You want its loss or accuracy to keep going up. You also want the train accuracy to keep going up, but you want to stop training when the validation accuracy starts dropping. So the training accuracy will always keep going up because you're training it on that set. The validation, you're not training, but it's just a diagnostic. It will keep getting better, but after a point, you overtrain, and then the validation accuracy starts dropping. And when these start diverging like this, that's when you do early stopping criteria, and that's what you're seeing there. But once you train and you freeze it, then there is an actual test set which has not been shared with you. And the test accuracy here is 96.7%. So these are all good diagnostics that people use in machine learning all the time. And I'd like you to play with this piece of code, run it as is first, and very carefully start editing these models. For example, I could say, well, why do I need 64 filters? Can I make it 4 filters? See what that does. But once I make it, the code might break because I have to very carefully make sure that the rest of the code works. So let's see. So I made one layer to be size 64, right? So this became, let's look at the model summary. So now suddenly I have half the number of trainable parameters from 25,000 to 13,000. Let it run. Let the next stage run. 500 epochs, and I want to see the validation accuracy and the test accuracy. Those were in the 97% and the 96% after training. So let's see where we end up. So validation loss is fluctuating a bit, up and down, up and down. The validation accuracy is also fluctuating. Let's see if it settles. It's still only epoch 40, so it's still early in the training phase. But epoch 65, the validation accuracy is already touching the 90s. It's fluctuating still. It's going from 80 to 90 up and down. So let it stabilize and we'll see if it does an early stopping. So I find staring at these diagnostics immensely energizing. Makes it look like, oh my God, it's like being in an auto mechanics shop, right? You put on all these onboard diagnostics and you're visually checking if things are going well or not. And it's makes you feel good. So the sparse categorical accuracy is the training set accuracy. That's already gone to the 96% and the 97%. The categorical accuracy, which is the validation loss, validation accuracy is catching up. And an early stopping is when the validation falls, because it converges. It has to catch up, converge, and then it has to fall. Then we do early stopping. But let's see if those conditions are met in this case. Right? Epoch 158. It is going a little slower than I thought. So in the interest of time, I want to stop execution, but you should do this at leisure in your home. So interrupt execution. Let's see if it lets me interrupt. Maybe it will not let me interrupt. So now we're stuck. All right, validation accuracy is at 98 and the test accuracy is also at 98. So now it might start falling and maybe it will do an early stopping. Wow. So the question I'd like you to think about already is with half this model size, the previous model we started with had 25,000 parameters, and it reached about the same type of accuracy, 97%, 96% on the training set, the same rough value on the validation set. Now we're getting the same values, but at half the model size. So which one would you prefer? So there are some theoretical considerations to have, and there are some practical considerations to have. The theoretical considerations are models with large parameters tend to be more flexible in the sense that they may be able to be fine-tuned to new data sets more easily. But increasing model size also means they are slower to train and they need higher memory footprint to deploy on a wearable device, or even if you want to deploy it on the cloud, you have to have more computation power to run it. So it's always a trade-off between training costs and inference costs, which is how much time does it take to actually pass one test signal and get an answer. That's called the inference time, inference cost. and also the generalization capabilities. The last word has not been set in this world, but it's still a very rich area of investigation. Okay, so now things are at the 97%. Uh, I have a feeling it will do an early stopping now because validation accuracy seems to be falling a little lower than the test accuracy, I mean the train accuracy. Uh, uh, uh. There you go. It early stopped. So yeah. Now let's evaluate this new model on the test set. So these are the old numbers, by the way, right? So this 97% is, this 96.7 is the test accuracy from the previous one we did. So on the new one, we are also at 96%. So that is the question. These neural networks tend to have somewhat of an arbitrary structure in how we make the model. And you can get the same performance from half the number of parameters. You may get the same even with a quarter of what we have. So explore those things as part of the assignment. And that is where we are with time series analysis for classification problems in the post 2010 era, is what I'd say. I'd like to switch back to my presentation again, because I do want to talk about a case where we have improved upon neural nets with a good fusion of some pre-processing methods. I want to talk about one of those examples. And let's go back here. All right, so here we are back. So, the part of my research is on exactly this type of interface where we get access to interesting types of time series data from interesting new types of wearable devices that people are developing. What we find is the longer you wear them, the more challenging analytics gets because gaps in data, much more data to deal with. And as you wear them, the wear location changes. So that changes a lot in the time series. So how do you deal with all these variables? So one of the things we dealt with is what is called uh, temporal rate variations. So this is for good old-fashioned activity recognition from a wearable on the wrist, like a Fitbit, and maybe you're looking at classifying daily activities. So this is walking on a treadmill at 1 mile per hour, one tracing of that, and an accelerometer gives you three signals: an X acceleration, a Y acceleration, and a Z acceleration. Part of the problem is how do you deal with that? And in the neural network world, it's not hard. I mean, they can work with tensors, so you can take a three-dimensional time series and have a convolution that operates on the vertical section, no problems. That works very easily. But in the old ways, we would try to simplify it by looking at things like energy signals, where you would take the XYZ, compute a root mean square value, like square root of the x square plus y square plus z square, do that at every time instant. And we call that the energy signal. So these are energy signals of walking on a treadmill at 1 mile per hour and a 100 hertz device. And this is a 10-second recording, so 1,000 samples. And it's an overlay of 100 such recordings. So you'll see it's a jumbled mess. Now, it being a jumbled mess in and of itself is not a problem for machine learning. But if you want to understand why models don't work or why they work peculiarly in certain ways, you have to pay attention to the underlying phenomena and try to explain the observed variance in ways that can be accounted for, or if there is a nuisance variable, how do we remove it? So it helps to know a little more about why this variation exists as opposed to just putting into an arbitrary neural network. So there are many variabilities that affect time series data, especially of a variable nature like IMUs. There is intrinsic variability in how we perform actions. The same person, if I put the accelerometer, on a wrist and ask you to perform walking 10 times, the signals will look slightly different each time. We are not perfectly periodic in that way. That's just intrinsic variability in our bodies. If you take long recordings, sensors don't sample at fixed sampling rates either. So we've been saying things like, oh, hey, a 100 hertz device as if it's set in stone. But in reality, sampling rates work off of an onboard clock, which sometimes drifts. So 100 hertz can mean anything between 90 hertz to 110 hertz, and it may be dynamically changing through the day, which means, yeah, your signals will look wonky a little bit, just a little wonky because of that variation. And if you ask someone to wear the device and live their lives, that device is not sticking to their arm, it's flooping around. So maybe they shift the location to the other arm either, right? So there is variability in where the sensor sits, and that can also change the signals. And then body type, gender, demographics, just your stress levels, what else are you carrying on your back that day can change how you move, and that manifests itself in the signals. So one of the variations that we wanted to work on in a slightly formal capacity is called rate variation, or warps of the time axis, which account for things like variations in speed or even variations in the cycle. Even when we walk in the gait cycle, different phases of the cycle can be done faster or slower. So all those variations are called temporal rate variations. Now, of course, the neural network can deal with it. We can pump all this data and let it work with it, and it does well. But what we're trying to say is if you pre-process them a little cleverly, it helps the neural networks. And here are examples of what we can do. So this is a very classic approach in time series analysis called dynamic time warping, which is specifically designed to take two time series where the time axis has been played with in one of the cases and align them. And it's an old technique in speech recognition where you would build word recognizers by speech signals by matching two signals from one from a library, one from a spoken word, and do the stretching and shrinking of the time axis to find the best matching word. The same concept can be applied to IMUs, but we have gone way beyond that. We are now able to take stacks of signals, like the top left panel here, which are 100 recordings of walking, and do what is called phase amplitude separation, where this panel in the middle is called a time warp function. This is an estimation of how the time axis should be warped for the example signal so that all the given signals start aligning their peaks and valleys. So this is the cleaned up stack. These are the warp functions, which we have isolated from this unclean stack. And the benefit we see is now when you take averages of these signals on the bottom right, you see clean averages. The walking gait cycle is really nicely visible as a quasi-periodic signal. And the upper and lower, the red and the green are the standard deviations of this stack computed on a per time instant basis. And they are very neatly hugging the blue curve, which means we have reduced the noise variation, noise or nuisance variables. If you just did mean and standard deviation estimation without this pipeline, this is what you get on the bottom left, which is, yeah, the blue is not clean. It's not looking like a walking signal. And the red and the green are saying the variability in the stack is very high. But can machine learning still do the work of recognition? Yes. So we did an experiment on the 7 activities of daily living with and without this pre-processing step, and with good old-fashioned feature extractors, and then good machine learning methods like support vector machines, and then neural networks. And we find that things get better in both cases. So yeah, we used a 37-dimensional feature vector, which are computed through Fourier type methods, which I'll encourage you to read. I cannot cover all these definitions in this lecture. You take what is called a Fourier transform, and then look at a top few coefficients, and you can look at these XY signals and look at correlations between them. So they're all summarized in a set of 37 numbers. And the classifier we use is a SVM called a support vector machine, which is a linear classifier in feature space. What we find is, yes, methods do work well. I mean, we get 86% on 1,000 sample, input, and we can recognize that well. But as the window length shrinks, if you want more real-time decisions, you don't want to wait 10 seconds to make a decision. 1,000 samples here means 10 seconds, right? If you want a quick real-time method, you want to maybe have a smaller window. So when you have smaller windows, it gets harder and harder. You have less and less information to make a decision by. And all these variations make it harder and harder when the window lengths get smaller. So performance drops. But when you do our cleanup method, we find that we do consistently better, and we do much better when window lengths are lower. So those are the kinds of benefits we see. We can also do this with neural networks. where we have integrated a temporal warp estimation type module inside of a neural network. We call that a temporal transformer. And we hit it with a convolutional neural net, just like the one we coded up. And again, we find that when you do this learnable temporal estimation module, performance of the convolutional network improves. So by sometimes subtle, sometimes very significant ways. And the message is you should use neural networks now because that's becoming the standard. But as we demonstrated that in the neural network world, interpretation is hard and there is no gold standard model itself. There's many models, and within each model type, there is arbitrary choices being made in model architectures. It's very hard to say what is good, what's not good. But as that field progresses, it is also important to know how to improve the performance of neural networks without necessarily adding more parameters, but maybe using some of the older signal processing techniques to improve performance. So we are nearly at time and we went through a lot, and I will stop sharing now. And I will encourage you all to look at the assignment that we post and feel free to reach out. It's been a pleasure and thank you so much. See you all soon. Bye-bye.